Hello everyone, in this video I would like to show you how you can use Python and the SymPy library to derive the equation of motion for the simple pendulum. For those of you who are unfamiliar with what it is, it's basically a point mass hanging down from a massless rod whose length is denoted by L, and then you have this theta angle right here. It's basically the deviation of this pendulum from its rest position, which would be for theta equal to 0. So this is the idea. We have the x-axis here, the y-axis here, so we can express the position of this point mass in 2D. Okay, so let's go through the cells here of this script. First of all, I'm importing, everything from the SymPy library. May not be the best idea if you're dealing with multiple modules, but for now, I think it's just easier. So import everything from SymPy, and then from SymPy physics mechanics, I import a class called Lagrange's method, as well as a function called dynamic symbols. And this is for display purposes, so it's not really relevant to the rest of the code, but it just will let us see our results in a nice form. So first of all, we have to define the necessary symbols and functions. In this case, we define t, which is time, g for gravitational acceleration, M for mass, and L for the length of the rod. So over here you can call this function called symbols, and you can basically copy and paste what you have here to this side. And second part is, I define theta, which is the variable here. So I'm using the function called dynamic symbols, and here is the display name basically. So if you use something like LaTeX or LaTeX to display your output, it will use that corresponding Greek letter automatically. You could technically also define it as a function using the function class, but then you would have to include a t here like so. So this is probably easier, this approach that I'm using. So let's go through this here. Okay, sorry, I didn't run the first cell apparently. So now it should work, and actually I want to go back to dynamic symbols so that I don't have to worry about that t. And this is basically like a helper function here, which lets me display the left hand side and the let's call it right hand side of the equation. So let's go through this, and now we define the position of the mass point based on the angle. So we have to use some trigonometry here, the sine and the cosine functions. So as you can see, we can define it, we'll just pretend it's a right angle triangle, and that's what you will get. And here we're just going to display it right away to see where we're going and if it looks any good. Okay, so basically it's the same as here, but display it in a nicer way, because in my browser, so it can use mathjax to make this look pretty. Okay, so now it's time to compute the time derivatives, and we can use the diff function, but not like the one in the NumPy module, if you remember from my previous video, but the one from SymPy, which is like symbolic differentiation in this case. So basically you get the output function. So this is xd, which stands for x dot. So the first derivative of x with respect to time, and the first derivative of y with respect to time. Of course, in this case, using the Lagrangian approach may be a bit of an overkill. It's probably easier to do it by directly applying Newton's second law of motion. But however, I want to illustrate the whole idea and of the Lagrangian, and also how to use the SymPy module. Okay, so let's run this. So from sine we get cosine here, and also from sine over here. From sine we get cosine, and from minus cosine we get sine, because the derivative of cosine is minus sine, so it makes sense. And just remember to multiply it by whatever function we have inside this cosine function or this sine function. Okay, so now it's time to calculate the kinetic energy and the potential energy. Let me just maybe add this. So calculate the kinetic energy and the potential energy. Okay, so here we have the kinetic energy. So let's go back here. So this is like the full formula for the kinetic energy. We have 1/2 times mass times v squared, which is linear velocity, or if you're dealing with like a rigid body rotating about its center of mass, you may also want to use this part. However, in our case, we can represent everything just as a point moving on this plane, this xy plane, which is why we don't really need the second part. So the first part is all we gonna apply. So as you can see, it corresponds to that. So we have m times xd, which stands for x dot, the first derivative of x, and then the first derivative of y. So we square them and also divide by 2, because here we have this 1/2, this fraction. Okay, so we're also going to display those, and here I'm using a function called SymPy, which basically tries to make the output less verbose by finding some things it can simplify or reduce in some way. So this is all it's doing. Sometimes I use it just in case when I expect like a very long output. So it's probably relevant here. You can be more specific depending on what kind of simplification you need, but this is kind of like the jack of all trades when it comes to simplification, and it tries to find the right algorithm for you. Okay, so the potential energy is pretty easy. You just need mass, gravitational acceleration, and the height from your reference level. And in the case of the Lagrangian, it doesn't really matter where this reference level is. For example, it could be here, doesn't really matter. So what really makes sense in this case is just to assume it from the horizontal x-axis anyway, because we already have it, so why not? Okay, so let's run this part, and we get the kinetic energy as well, the potential energy, and now the Lagrangian. So to put it simply, we just subtract from the kinetic energy, we subtract the potential energy. I'm also using the SymPy function, so it can make the output look less verbose. Okay, so let's see what we get from there. Okay, so it looks more or less like this. And now we're gonna use the Lagrange's method class here to get this output. I'm not even sure if you can do it like this. Maybe like this is okay as well. And you get those equations by using the method inside that class, which is called form Lagrange's equations, which are basically equations of motion. It's plural here, even in our case it's singular, but it still returns some kind of array or list. So if you just want to grab this first item from the list, you need to specify the index here. So for example, 0. And of course, we display what we get using this helper function that I defined earlier. So yeah, this is what we have here. So let's try to run it. Something went wrong here, so it should be square brackets here. Okay, so this is what we obtained. So this is our T, which stands for torque, basically. So it basically tells us, what torque we apply to this structure. For example, in order to make it move. If we don't apply any torque, it will just, in this case, like oscillate back and forth, basically forever, because there's no, damping or any sort of friction included here. So it will be like perfect oscillation over time. Okay, so this is the equation of motion that we got from there. And in the case where we assume this torque to be 0, so there's no torque applied to our structure, to our system, then we can simplify this equation. We basically solve it for the second derivative of theta, which is theta dot dot, and also we have to grab the first element from the resulting array, and also we display the result here. So as you can see, we get theta dot dot equal to minus g sine theta of t divided by L. Sometimes, when the angle is really small, this function is omitted, so it looks even easier. As I said, it's a pretty simplistic example, but hopefully it illustrates the idea of how you can use SymPy, the SymPy library in Python, to derive equations of motion. In this case, it's only one equation because we have 1 degree of freedom, so one generalized coordinate applies here. Only one. Okay, so I hope you find this video useful. And maybe I just forgot to tell you that this equation of motion basically describes how this pendulum moves, like due to it, like because of its own weight, or because of like torque, some torque applied to it. So this is in simple terms how you can derive it. So again, hope you find this useful. If you do, like this video, leave a comment, subscribe, and hope to see you here again for more content. So take care and bye.